Hey Shane,
How are you?
doing all right.
Awesome.
Looking forward to Thanksgiving.
Oh yeah, me too.
I can't wait already
Yep.
to go back home and stuff. Yeah. Um, but I've been doing section bank.
Mhm.
And we actually have like a session tomorrow,
Mhm.
and I wanted to go over some stuff from that. What I ended up doing though, actually yesterday, I've been doing section bank like or been trying to every day since we last met, but yesterday. Um, I like retook the Chem Phys section of AMC full length one.
Mhm.
Um, what I think I'm gonna do is, I mean, I took full length one in August, but I remember like we reviewed some of it, but I never thoroughly actually like reviewed the exam and made flashcards and stuff. Um, so I retook Chem Phys yesterday, so I can like go through it again and this time a little more in depth.
Mhm.
And I wanted to go over a pass from that today.
Yep.
Um, And then tomorrow we could focus on the section bank.
Okay.
So give me a second to pull it up. Do you think like the full length um like the curves, I guess, they're harsher because they're harsher than blueprint because just like the actual MCAT is a little easier, so the curve ends up being a little harsher than easier than blueprint, sorry.
Sorry. Say that again. Easier or hard?
Okay, so like on the actual AMC full lengths, I found that the curve, so like the amount of mistakes you get wrong, let's say it's 10. Let's say you get 10 wrong, you're gonna get a lower score on AMC as opposed to if you get 10 wrong on Blueprint, you know?
Okay. Yeah, I never actually compared the two like that.
Oh, okay. I was just wondering, but
But are you saying that you did and then you found that you can get more questions wrong on the blueprint? What?
exactly. You get more wrong on Blueprint,
Huh? Yep.
and yeah, I mean, I was just wondering. Whatever, it's not important. I should be thinking about it anyways, like that. So yeah. Okay. Um, so this passage is my favorite. It's electrolytic cells and like galvanic cells.
Okay.
So yeah,
Um, okay. Let's have you read out loud.
sure. Okay. A group of students investigated the reactions of several metals with solutions containing metallic ions. The students placed strips of a metal into solutions containing different metallic ions, as shown in figure one. Um, After several hours, they observed whether or not Y solid formed on the surface of the metal strip.
Okay. So let's take a look at this table. Results of metal strip experiment. We have identity of metal ions in this first column, and then we have composition of metal strip, like the rest of those columns. And what do you think so we can see that if they have so okay, what do you observe here?
I mean, there's two different metals.
Okay.
One of them is like dissociated in water. It's like an aqueous solution.
Okay.
And then the other is in solid form.
Okay.
And there could be a redox reaction that ends up happening between
Uh-huh.
the solid and the dissolved metal.
Okay. What's up with these?
Oh, table two. Okay. Um, Well, it says not studied for the asterisk.
Yeah. Um, but I'm saying, do you notice anything about these?
I mean, the aqueous of like the same elements
Huh?
weren't studied.
Yep.
I guess they're not reacting with each other. Because I mean, like,
Yeah, so they're
because that's
not.
like it's the half reactions, like the Cu2 plus and the Cu, they're in the same half reaction, right?
Oh, it's just that in this experiment here, X solid is different because like this ion, if it was the same, it would be like XM plus, right?
Yeah, okay.
But since it's Y, it must be different. So they never actually did it with let's say an aluminum solid strip and an aluminum cation. They
Hmm.
never did anything where they're the same.
Okay.
That's why it says not studied. Good. Now, what about something like this? So that's when you have a copper strip, metal strip, and aluminum 3 plus cations. What does it mean, no change?
Um, the copper didn't, you know, form anything.
Yeah.
Sorry, there was no
Mhm.
aluminum forming on the copper.
Yeah. Good, good, good. And what about like a new solid?
I guess that would mean that there's copper forming on the surface of the zinc metal strip.
Okay,
So there's a redox reaction happening.
very good. Okay, you can continue reading.
The students placed a solid strip of metal into an aqueous solution containing ions of the same metal. Complete circuits were established.
All right, so now we see X solid on the left, Y solid on the right, and then we have the X cation on the left, Y cation on the right. Um, and the deal, like, if let's say X solid gets oxidized, it should be sending electrons through this cable to the Y solid, which would get reduced, right?
Hmm.
Okay, continue.
Yeah. Finally, the students checked the general chemistry text to determine the standard reduction potentials for the following reactions. And then it gives us the reactions.
All right, now are these reduction half reactions or oxidation half reactions?
Reduction.
Okay. Now, between the lead and copper, which one is likely to be reduced?
The copper,
Why?
high reduction. Like sorry, higher electric potential.
Reduction potential?
Reduction potential.
Good. So that must mean what for the lead?
Well, that means the lead gets oxidized.
Okay.
The thing
So,
is, though,
yeah.
this is what I was wondering. How do I know if it's a galvanic or electrolytic cell with just this information? Because, you know,
Well,
because, yeah.
yeah. So a an electrolytic cell is going to have an external source of electricity.
Oh, right. Okay.
A electrochemical cell, like that's literally what a battery is.
Yeah, yeah, yeah.
Hmm.
Yeah. And the light bulb also helps, right? Like we see
Oh
the
yeah,
light
it's
bulb.
not just like if a way for us to see that electrons are moving from one to the other.
Okay, got it.
Okay, now what happened to the lead? You said what went?
Okay, so reduction potential is higher in the copper. That means higher. I mean that means copper is gets reduced, which means the cathode. Lead is the anode.
Which means
Uh, there's oxidation happening at the anode.
yeah. So what would that reaction look like? Would it look like what they wrote here?
Well, they'd have to, you flip the lead equation.
That way, right?
Yeah, correct.
And then what would the oxidation potential be?
It would be flipped too, so it'd be 0.127 volts.
Yeah, positive, right?
Correct.
And then your cell potential would be the sum of these two, right?
Um, y yeah, technically, yeah.
Uh-huh. And that would give you a positive value, which would give you a negative delta G, right?
We're right. Yes.
All right, cool. So, all right.
I have a question. So in the art, if they showed it, I guess being connected to like a wall or something, that's where you think, or that's where you would know that it's electrolytic, right?
Yeah, it would be like connected to like a separate battery or something like that. Yep.
And would that eventually happen, like after X amount of time? Like you would need to somehow power it with the.
Yeah, so after enough electrons have left the lead and reached the copper, you're going to get your equilibrium, like your dead battery.
Mhm.
And then you'll need, in order to charge it, like to charge it again, you would plug it into an external electric source. And that's when you get your electrolytic cell. So that's when you charge it. Yeah. Or we.
Okay.
Hmm.
All right.
Yep.
All right. Well, I guess we could try the question, right?
Go. Yep. You could read it.
Okay. When a strip of zinc is placed in a beaker containing 0.1 molar HCl, H2 grams evolves. I mean, sorry, H2 gas evolves. If a strip of aluminum is placed in a beaker containing 0.1 molar HCl, does H2 evolve? Okay.
All right. Let's think about what they mean by this. Um, okay. So the reaction between zinc is with what first?
HCl.
Okay. And the HCl turns into H2 gas. What's the significance here?
Um, well, HCl dissociates, right?
Generally, but if it dissociates, you would get your H plus and your Cl minus. But this has H2 form. So, and, the choices all say stuff like redox, so likely redox is happening.
Yeah.
So why don't we look at oxidation states?
Oxidation states.
Yep. Meaning for HCl, what's the oxidation state of the hydrogen?
+1.
What about for H2 gas?
0.
So what's happening here?
Um, you're gaining electrons, so reduction.
Reduction, right? And zinc would have to be getting um
Oxidized.
oxidized, right?
Correct, yeah.
So this must mean the reduction potential for the hydrogen, is it larger or smaller than the reduction potential for zinc?
It would be larger.
Yep. Okay. Now they're saying if a strip of aluminum is placed in a beaker containing, the same amount of HCl, does H2 gas evolve?
Hmm.
So what can we do here?
I mean, do we need to know the um oxidation state of aluminum or the reduction maybe? I don't know.
So
But we have the table.
yeah,
Um, but that's all I can really think of.
okay. So what can we use in the table?
Um, there's zinc oxidation states.
So
Well, charges, but
okay, when we first saw the table, we saw that the significant part of it is whether you have no change or new solid, right?
hmm
Because that indicates to you that redox is happening, right?
hmm
Okay. Now, there isn't any way for us to directly compare like aluminum in this case to the hydrogen.
yeah.
So what we can do is we can compare the aluminum to zinc.
hmm
Because if aluminum has a lower reduction potential than zinc, it must be true that it has a lower reduction potential than hydrogen, right?
hmm
So, so let's see, right?
Okay.
So let's say you have a zinc solid and an aluminum ion. What happens?
Yeah, there's no redox reaction happening.
Good. Now,
Um,
what if we had an aluminum solid and a zinc ion?
new solid.
New solid. What do you think that new solid's identity is?
Um, wouldn't it be aluminum with zinc on it?
So, what's like the half reaction there?
Um, the aluminum gets reduced.
Well, what would that new solid be composed of?
Aluminum and zinc.
So, but the new solid part, because the old solid is aluminum,
Well, zinc.
zinc, right? Zinc would be the new solid.
Yeah.
Now, would that be so? Would zinc get oxidized or reduced?
Um, well, I thought oxidized.
So, okay, so zinc solid has a charge of,
Zero.
okay, so if you go from zinc 2 plus to zinc with a charge of zero or an oxidation state of zero, what are you doing there? Are you doing,
Uh, reducing.
yeah, because you're adding electrons, right?
Yep.
So when you have zinc and aluminum, zinc is the thing that gets reduced, right?
Hmm.
So what can that tell you about the oxidation state? Or sorry, what can that tell you about the reduction potential of aluminum?
It's lower.
Lower than?
The zinc one.
Now, if it's lower than that of zinc, and zinc's is lower than that of hydrogen, then it must be true that the reduction potential of hydrogen is greater than the reduction potential of aluminum, right?
Hmm.
Okay. So what answer would that lead to?
B.
Hmm. Because hydrogen has the higher reduction potential, so it gets reduced, and aluminum has a lower reduction potential, which means it gets oxidized. And yes, H2 gas will evolve.
But the thing is, like here, like when you have this reaction that happens,
Uh-huh.
um, I, I just don't understand. Like when you gain electrons, aren't you forming a solid? Like you're,
Uh-huh. If you're the ion, yeah.
but like here, if the X reacts with the Y
Uh-huh.
and the Y ions start forming on the X, isn't there some of the X still left?
Yeah.
Like it would be X plus Y.
Yeah. So you're having the Y ion turn into a solid, and you're having the X solid turn into an ion. So you're actually losing. Did I forgot if it was you or a different student, but there's like a picture of
It's
like
me.
with a, and you know what I mean, with like
Yeah, yeah.
little holes.
You love that picture, I think.
Yeah, yeah, yeah. That was a good. That was a really good picture. But
Yeah.
that showed holes in it, right? So
Yeah.
you would have whatever X is lose some of that metal because it turns into the cation, and you'll have some of the Y solid add on to it.
Okay.
Yep. So,
Yeah, so I missed the part where the X turned into ions.
oh,
That that makes sense more now.
yeah, but I mean, for this question, it doesn't seem to be. Oh, by the way, did you get 52 right? Because it seems like this starts at 50.
Yeah, 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 I did.
Got it.
I mean, honestly,
Uh-huh.
like, because I know it's D, and I did just like, I just knew this was a lock to be right.
That this is.
Um, like I knew for sure that it would be right because it made sense. Like we decrease resistance, we increase current then. But I wasn't really sure what the other options even like would do. So I guess we could maybe go over it.
Yeah, that's important. So, um, did I ever like draw like a wire like that?
I don't think you have.
Okay. So, you're gonna have your regular wire with like that's made of copper.
Okay.
It has a lot of these copper atoms, and your electrons, in order for it to be electricity, goes, through them or brushes up against them. Okay.
Hmm.
Now, let's say that this is a side view, and we have these atoms. So the electrons, as they travel, they brush up against these copper atoms, producing like a type of friction. And friction, it's a non-conservative force, which means that energy is lost to the environment in the form of heat. And resistance, when we're talking about in a circuit, is that. It's basically like you're losing energy in the form of heat. And if we see that this is longer there's going to be more copper atoms that the electrons will brush up against, right?
Yeah.
Now, let's imagine if it was wider, okay?
Hmm.
If it's a larger cross-sectional area, there's more like kind of paths for the electrons to travel through, right?
Hmm.
Meaning less resistance. It's almost like, let's say this is um like a subway and it's like narrow and it's long and you walked, from one end to the other, you're gonna brush up against a lot of people. But if it was like a wider type of thing, there's more paths for you to go through that won't cause you to brush up against the atoms,
Hmm.
right? So that means that resistance is rho, which is something called resistivity. It's just a constant.
Yeah, yeah.
Yeah. And length on top over area on the
Yep.
longer it is, more friction, more resistance, and then inverse for the area. Now, this shows itself in resistors. For instance, these two resistors are in series, right?
Yeah, they are.
And if you combine them, you get the equivalent of just a longer resistor, right?
Hmm.
And if you have a longer resistor, resistance goes up, right?
Yes.
So that's why for if two resistors are in series, you simply add the two resistances to get a
Hmm.
larger one, right?
Hmm.
Now, if we had resistors in parallel, right? The electrons can go in both of these directions, right?
Sure.
And that creates if you add these, it creates the equivalent of a wider resistor or a resistor with a larger area. And if it has a larger area, the resistance goes down. That's why you have a reciprocal sum. A reciprocal sum is going to be smaller than either of these on their own. And since in a parallel circuit, the resistors that are in parallel are the equivalent of increasing the area, right?
Yeah.
So that's why the formula is what it is for adding resistors in series and adding resistors in parallel,
Hmm.
right? And it's the opposite of capacitors. Capacitors get larger the larger area you have.
Yeah.
And they get smaller uh, based on the distance between the plates. So that's why capacitors in series is like more like increasing the distance between the plates, and that causes a reduction in capacitance.
Yeah.
So in series, capacitance, if you added them, you would use the inverse reciprocal sum. But if you had capacitors in parallel, you're increasing the area, and therefore you just add the capacitances for each.
Hmm.
Okay. So okay. So if they're asking increasing the current, right? If you used electrical wire with a smaller diameter, right? You are uh decreasing the area, which means that the overall resistance is going to go up or down.
If you increase the area or decrease. If you decrease the area, then resistance will go up.
So if you used a smaller diameter, you would have a smaller area.
Yep. And then resistance will go up.
Good, 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 good.
And that will decrease the current, so A is wrong.
Exactly. And then B, temperature, that's what happens when resistance happens. Like heat is lost to the environment, right? Which means that it gets hot. So B, increasing the temperature of the electrical wire, that is what you would have happen if you have an increase in resistance, which means that B would not work, right?
Okay. So you're saying when you have increased resistance, there's increased heat.
Exactly. Because resistance is at its fundamental level friction.
Okay. I'm gonna make a quick note of that.
Mhm. But yeah, it helps a lot to instead of just knowing like the formulas to like know
Yeah,
why.
how they're derived, right?
Yeah, and then also just knowing like a reciprocal sum will always be smaller. It's like if I had an object distance of 4 and an image distance of 3, my focal length, let's say we had A, B, C, and D. Let's say we had like 8, 12, 5, and 2. Like without doing the math, what would be like the best choice?
Oh, D.
You said D?
Um, wait, hold up. 1/3. Well, it'd be 1/3 plus 1/4 equals 1/x, right?
Oh yeah, yeah. I didn't do the math part, so let's not think about that. But let's think about what I said about a reciprocal sum having to be less.
Like B.
You said which one?
So you're saying like there's
Hmm.
like if you add these two together, it would be so D, right?
D. Yep. Because the thin
Opposite.
equation is another invert reciprocal sum.
Yeah,
And a reciprocal sum will be smaller than each of the things that you're, adding.
yeah. Okay. So in terms of B, if you increase the temperature, um,
Hmm?
this is it true that increasing temperature like increases resistance
Yep, and vice versa.
and vice versa? Okay, that's what I was getting at. All right, gotcha. Like that. Um,
Yep, and if you decrease the concentrations of this stuff, you'll
mhm.
have less of the redox happening, which means you'll have less of the electrons traveling and therefore less current. And then D, replacing the light bulb with one. I mean, did they originally say the light bulb was higher than that? I'm guessing. Because yeah, if it's
Yes, correct. It was
okay,
zero
okay.
point 0.5.
Yep. So if you reduce the resistance and you keep voltage same or so yeah. So yeah, that'll be D.
And you said resistance at its fundamental core is friction.
Yes, yeah. And just like friction causes heat to be released, right? Same kind of deal.
Okay.
And that right there.
What again is a non-conservative force?
So um on that boat's Democrat. No.
Hey, you already used that before.
Yeah, I did.
I remember.
I
You
think it's
just yeah,
with DNA, semi-conservative or something like that.
probably. No,
But
you said conservative votes Republican. That's what
yeah,
you said
yeah.
last.
So so basically what it means is that energy is not conserved because energy is lost to the environment as heat.
Wait, repeat that. Sorry.
Yep. So So non-conservative force means that energy is not conserved, and that's the case with friction because energy is lost to the environment in the form of heat.
Okay.
Yep,
Energy is not conserved.
correct.
All right. 1 second. I'm writing a no. All right.
All right.
So assume that a circuit similar to that of figure 2 set up in which x equals AL, x sine 2 plus equals AL 3 plus, y equals CU, y plus equals CU 2 plus, which of the following reactions will occur?
Okay. So how did you approach this?
Um, Man, I think I looked at the table.
Yep.
Um, I also wait, yeah, never mind. So I looked at the table
Okay.
and right, I also remember that I eliminated B right away.
Why?
It was balanced like incorrectly.
I see, I see. So what would we be looking for in table one?
Oh, in table 1, we would look at the AL intersection with CU.
Okay. So if we had Cu solid and aluminum ion, no change, right?
Mm-hmm.
And then what about aluminum solid Cu ion? New solid, right?
You saw, yeah.
What does that mean then?
That like it's gonna turn into CU solid.
So what does that mean?
Um that CU is getting oxidized.
So Cu 2 plus and
Wait, hold on. Wait, no, it's getting reduced.
yep, because we're going from Cu 2 plus to Cu.
Yeah, yeah, yeah.
So we know that copper gets reduced. So we would want Cu2 plus on the left side, right?
Yeah,
So we can get rid of these, right?
yeah.
Okay. Now I guess it's a matter of the right balancing it right.
Yeah. Um, there'll be C.
Yep. Okay.
Yeah. We went over this, I guess, is like the beginning. Um, it would definitely occur spontaneously, and like, yeah, we already got the E of the cell. It's D, right?
So, oh, so, um, yeah, even if we didn't do that, we would still be able to eliminate two choices, right?
Yeah, I mean, because we just know that like spontaneous is when the E cell is positive.
Uh-huh.
So like C would be wrong.
Yep.
Um, and then B would be wrong.
Yep. Good.
Okay, and this was like rudimentary, like V equals IR,
Hmm.
right? Um, let's
That
see.
wasn't too bad.
Yeah. So I was wondering,
Yeah.
let's check.
I think the only hard part about this was like the table and understanding
Yeah,
that new solid meant that the ion gets reduced.
right. I was a little confused about this. It's from a while back, but
Mhm.
I'll ask you now that we have some time. Um, I guess how like conductors work.
Initially uncharged solid conductor is placed between the plates of the cell membrane parallel plate capacitor. The electric field inside the solid conductor must be, I think this is like a what a dielectric does. Initially uncharged solid conductor is placed between, okay. Say something.
Well,
Mhm.
um, if anything, I'll just maybe we could revisit this. I don't know.
Yeah,
Um,
sure.
you're like not sure.
Yeah. All right, we can come back to it.
Okay, so the something else I was gonna ask. So with here, one second. See the Anki.
Uh-huh.
With like the
Oh yeah.
with when like the electron falls from a higher to lower energy,
Yeah. This is a yeah, go on.
it emits light, right? And my question is that what fluorescence is called? Is that fluorescence? And then color
No.
is what we perceive that fluorescence to look like. So like what is the difference between color and fluorescence? And do I even have the correct idea?
So so okay, this is a good high yield topic to talk about because like there's three scenarios here. Now, I
Uh,
usually yeah. So first of all, okay, let's say so so okay, let's say that we have, our
sorry.
okay, let's say that
Like yeah.
okay, let's say that I see what you're doing. Okay. The so the energy difference between the n is equal to 1 shell, which is the ground state, and the next excited state, n is equal to 2, is the 1 electron volt. And then between 2 and 3 is zero point 0.5 electron volts. If we shoot a photon with 0.99 electron volts, what happens?
Nothing.
Why?
It's not enough to excite it.
What if we shot 2 with 0.99 electron volts?
Um, I don't know.
What do you think?
Uh, wouldn't happen. Nothing would happen.
Why? Won't they just add up?
I think it has to be the same one. Like,
So something that they like to ask is like in a scenario like this is like, okay, what can we do to make it so that it is absorbed? And a choice will always be like increase the intensity. Now, would that work?
I mean, when you increase intensity, you're increasing the number of photons emitted.
Okay. So would that
But
work?
we just said the number doesn't work. When
Good,
you,
good, good, good. Because it's all or nothing and they don't add up. That's why it's called quantum mechanics. All right. Now let's say we shoot one with 1 electron volt, right? It'll take an electron and excite it up to the n is equal to 2 shell, and it'll eventually go back down to its ground state. And when it does that, it'll emit a photon with 1 electron volt as well. It'll be exactly the same energy. Okay.
uh,
All right. Now, if we have some molecule that has a lot of conjugation, something like this, that imparts stability to that molecule, right?
yeah, yes.
Okay. Now let's say that we shot a photon with 1.5 electron volts. What'll happen now?
It's gonna um give off an emission of light.
Well, right now, light is going at the atom. So,
Some energy is emitted.
okay. In this original example, this one, we had when we shot the photon at the atom, it can absorb it, and it expresses that by exciting an electron up to the n is equal to 2 shell. So that means it
Mhm.
absorbed the photon.
So go to n equals 3.
Yes, it absorbs it, right? Now, due to resonance stabilization, it will enable the electron to, let's say, drop down to the n is equal to 2 shell without needing to emit a photon. It can do that just through its own resonance stabilization.
Okay.
But now, when it's at n is equal to 2, it can then go back to n is equal to 1 the normal way by emitting a photon, except this time the photon's energy will be what?
1.5.
So if it's going from
Just 1.
1, right? That's fluorescence. Fluorescence involves the energy of the photon absorbed is greater than the energy of the photon emitted. So, in other words, the wavelength of the photon absorbed is less than this looks like an X, is less than the wavelength of the photon emitted. So, fluorescence will typically say something like excited at 360 nanometers and emitted at 420 nanometers, something like that. So yeah, that's what fluorescence is. And if you ever look, like, that's what uh pigments do and dyes. Um, melanin,
Hmm.
that's what happens with that too. And also UV vis, UV
Oh,
spectroscopy.
UV vis is another thing I was actually gonna ask you about. So,
Same thing. So it's a way to check for conjugation, because that's why if you're like like darker skin with the melanin, the UV radiation that comes in gets absorbed by the melanin, but then emitted as visible light. And that's what happens with UV vis. You if you have something with conjugation, it's gonna show, like that it's absorbed by the UV is absorbed and it can emit the visible. So essentially all this just means that molecules that have a lot of conjugation undergo fluorescence, which means that it's the energy of the photon emitted is smaller than the energy of the photon absorbed.
mhm. But how do we know when, like, how do we know that from N3 to N2, for example,
Mhm.
nothing would happen? Like, how do we know if it has resonance that happens or?
So let's say it didn't have resonance. If it goes from N3 to N2, it will have to emit a photon of that same level. So this is actually a good example of conservative versus non-conservative again, because fluorescence involves is non-conservative, meaning the resonance stabilization allows that excess energy to dissipate um, rather than being conserved. Because when we had the 1 electron volt, that everything is conserved there, but for fluorescence, energy is not conserved. That's why you have a larger energy of the photon that gets absorbed compared to that which gets emitted. If fluorescence didn't happen, it would just go like that and emit a 1.5 electron volt photon. Right.
So then is fluorescence like, so it's when light is emitted, um, when the energy of the photon, you said absorb,
Yeah, it's like okay,
is,
like you're the atom or the molecule, and it's like, okay, here's a bunch of energy, and you get all excited and stuff because it's like the electron's excited, but you feel a lot of kind of anxious and stuff. You don't really like having a high energy because things don't like in general to have high energy, like to be stable, which is low energy. So it's gonna want to give that electron back. But for fluorescence, it's like, okay, you give it the energy and it gets all excited and it like does some Zen meditation to let you go down to like a lower excited state. And then, you're less anxious. It's a way to dissipate that excess energy. So, so fluorescence you can think of as it absorbs a photon, it dissipates some of that excess energy through resonance stabilization, so that when it does emit a photon, it'll be of a lower energy level.
And is color what we perceive?
So color is just light that's in the visible spectrum. And, UV vis can do that. It can be like you shoot UV light at it and it gives off like a color. But yeah, color is just light in the visible spectrum that we can see.
And so energy photon absorbed is greater than the energy photon released.
For fluorescence, yep. And that this happens with molecules that have extensive conjugation.
Yeah.
You see that worded in a lot of you'd see it worded with pi, a lot of pi bonds, electron delocalization, conjugation, resonance stabilization, all those terms.
Mhm.
Now, the last scenario is photoelectric effect.
Yeah, but that one, I think, we're gonna leave it with a beautiful cliffhanger.
Uh-huh.
Because tomorrow's like session
Yeah.
is this. It's a section bank. It's a CP, the second passage in the section bank. I don't know if you remember, but um, that has something with the photoelectric
Photo,
effect.
yeah, yeah. Just really quickly, right? It's
Sure,
basically,
sure, sure.
let's say we have a photon with 2 electron volts. Okay. Now, 2 whole electron volts. So now the electron isn't just going to get excited to its outer shell. It's going to exit. It's going to get ejected
Mhm.
from it. Kinetic energy of the electron is equal to energy of the photon minus the work function. Work function is the ionization energy. So if you have energy that's higher than the ionization energy, you not only excite the electron, you eject it. And that's to bring it back around. That's what ionizing radiation does.
Yeah,
Yep.
but that's bad. It's bad, right?
Yeah, it's not really nice for living things like us. Uh,
Hmm.
but yeah. So those are the three kind of scenarios. So I would, in a nice kind of Anki way, let's see
Hmm.
what I can write. So I would write um normally normally energy of photon absorbed equals energy of photon emitted. If you have a dye slash pigment with lots of conjugation, the energy of the photon absorbed is greater than energy of the photon emitted, and this is fluorescence. And if energy of photon exceeds work function in parentheses ionization energy, um, electron is ejected out of the atom. So, oops. This is, I'll put it like there.
Mhm.
So normally, energy of the photon that's absorbed is equal to the energy of the photon emitted. If you have a lot of conjugation, then you'll have fluorescence, and then yeah.
Okay.
Yep. Okay.
All right.
Awesome. So, yep, I will see you tomorrow at 6:15 Eastern. And it'll just be, 75 for today.
Sounds good. You said 6:15?
Yeah, I have you down at 6:15, maybe. Is that wrong? Should it be?
No. I mean, I thought it was 6. If 6:15 is better for you.
No, yeah,
Is it?
I can do 6. I think I put
6?
that in because you had something and then it takes you a while to get something. I don't remember.
Gotcha. I should be fine with 6, I think.
All right. So 6.
Mhm.
All right. Awesome.
Okay. I'll see you. Have a good night.